used inverse trig functions before? To find angles whenever we were using our trig functions for sine, cosine, tangent, and everything, right? All right, we did that before a little bit. So now let's just look at it. We've been looking at the graphs of them. So we're going to start this off by looking at them just a little bit graphically, then we're going algebraically. All right, so first off, what's the inverse sine function? The inverse sine function is denoted by sine to the -1, and is the inverse of the restricted sine function, y equals sine of x, from -π/2, less than x, less than π/2. Thus, y equals negative sine of x means the sine of y equals x. So you can kind of rewrite it. It's almost like, remember back to like logarithms? You had that pattern, you could rewrite the logs with it. It's kind of similar to that. Or you just take the x and the y's, flip flop them, and change the sign of the negative, the sign of the sign. Okay? All right, that sounds a little funky, right? But let's look at it in graph function real quick. I'm not going to ask you to graph inverse functions, okay? I just want to show you kind of what happens for these. So if I am graphing my sine function, remember the sine function looks kind of like that, right? Now, if I wanted to find or actually graph the inverse function of sine, and say I'm worried about this point here, it would look something like this. It would be doing like the exact opposite shape, okay? That's what. So this would here would be the inverse sine. This one would be the sine. Okay, it's just kind of like the opposite shape. Because what we're doing the opposite operation. We're just working backwards whenever we use the inverse sine function. All right. Now, we got a couple different options. One, we did it before. We'll do it some more tomorrow. You have inverse sine. What do? Punch in the calculator, right? Well, what's happening in the calculator when we do it? Okay. So here is kind of your reference chart for this. So if you want to find an exact value, so remember, every time we punch in the calculator, we're finding an estimate, right? Unless it gives us one specific number, it's actually an estimate. Because it's going to be a decimal, it's going to go on forever, it's going to be a little ugly. All right, right here, if we want to find the exact sine values, the exact values of sine of the inverse sine of x. Sorry, I can't even talk today. All right, set it equal to theta to start with, then rewrite it. All right, rewrite it as sine of theta equals x. And you have to make sure it is within those constraints there. It has to be from -π/2 to π/2, because that's where pi is defined on our cycle. All right, use the exact values in the table to find the value of pi in that cycle that satisfies sine of pi equals x. So if you would look back to your unit circle even, and you would compare all these values. Okay, if you had your unit circle laying out right now and you looked at pi/6 and you want to find the sine, you're going to get 1/2. Okay, you would get pi/3, you would get √3/2. And way back in 40s, 50s, 60s, those before calculators really became a commonplace thing, what they would have would be these giant sine, cosine, tangent tables. They were trig tables. They were these cards that were about like this. They would hang on the wall, and there would just be all kinds of little tiny numbers. Okay, it would be a complete pain. Then you would have to try to memorize them, maybe up to like a pi, then try to multiply in your head. Right? That's how they used to have to figure these out. This is just a very, very minor snippet here. Okay, but this is going to be the ones that we would need. This is within that range of -π/2 to π/2. All right, so we can use this then just to find an exact value. So what we want to do, scroll down a little bit to this example. We're find the exact value of sine, inverse sine of √2/2. Okay, so here's our process. Start with that, set it equal to theta, rewrite it, and switch theta and x as also switch from negative inverse sine to regular sine. Make sure it's within this range and solve it. All right, so if I have this guy here, first off, I want to rewrite this guy. I want to rewrite this as the sine of √2/2 equals x. Now, the whole process sounds really confusing. I'll dumb it down as much as possible. If you want to find the inverse sine of root 2 over 2, go to your sine chart, look in this bottom line, and see where you get root 2 over 2. Where do you get it at? Pi over 4. Guess what? The inverse sine of root 2 over 2 is pi over 4. Bingo. So what this is actually saying, though, is the angle in this constraint, pi over 2, pi over 2, sine is root 2 over 2 is pi over 4. All right. Now, why do we put that constraint on? We put the constraint on because sine is cyclical, right? It goes up and down and up and down and up and down. It's like the tides at the beach. All right. If I stand at one spot today at the beach, eventually that water's going to hit my feet coming in, right? When it's going to hit my feet, going back out. Then what's going to happen the next day? It's going to do the same thing over and over again, right? Same way with our sine function. It's going to hit pi over 4 going up, then coming back down, then going back up and coming back down. So we would have basically infinite values of this, right? That's why we have to put that constraint on there. All right, so you would go to your sine chart, see when the sine is equal to this, work backwards, get the angle that goes with it. Second one, do it real quick. What is the inverse sine of root 3 over 2? Emma, you got that one for us? Maybe? Okay, look at your thing. Where do you see root 3 over 2? 5 over 6? Yeah, look at sine. Make sure you look at sine. 5 over 3. There you go. Whoa. The angle in that range from negative pi over 2 to pi over 2, whose sine is root 2 over 2, is pi over 4. Where? Definition. Right here. Definition. All right. For sine, yes. Cosine is slightly different. But sine, yes, it'll always be the same constraint for sine. Always be the same constraint for cosine. We'll see that's 0 to pi here. Okay. Same way with tangent. It'll have a standard constraint as well. All right. But then at the end of the day, I just wrote this out for the explanation of what I actually just found there. If I give this to you on a quiz or test and I say find this, all you have to do is write this. All right. So let's look at a cosine. We have another chart. Okay. Same thing with cosine. Set it equal to theta. Rewrite it. Make it cosine of theta is equals x. All right. We're finding theta. Now our constraint for cosine is going to be from 0 to pi. Again, it's a width of 1 pi. But we have to look at it just at a different constraint based on the values of it. All right, here's that whole list. Again, if I would go through, use the unit circle, find the cosine of pi over 6, the cosine of pi over 2, whatever, I would get all those values on the bottom. Okay, so this is just a reference chart. These are things that you could come up with on your own if you had to. So, look down here. Find the exact value of the inverse cosine of negative root 3 over 2. Where do you see that at? That guy at? Right here, 5 pi over 6, done. Next one, Exact value of inverse cosine of negative 1/2. Where's that one at? 2 pi over 3. Bingo. So those are pretty darn easy, aren't they? All right. It's just a reference thing. All right. Now, what's going to happen if I'm getting ahead of myself? Let's look at it for tangent as well. So tangent has the same constraints as sine, negative pi over 2 to pi over 2. Okay? Everything is exactly the same, just a different chart, different thing to reference back and forth to. Exact value of tangent of inverse pi of root 3. Where do you see root 3 at? Pi over 3. Bingo. Exact value inverse tangent of negative 1. Where's that going to be? Negative pi over 4. Bingo. Straightforward, right? And we could use those on lots of problems. Now, obviously, if it doesn't say exact value, it says approximate, especially when we're doing problems. We'll see this a lot tomorrow. We're going to solve for missing sides, solve for missing angles. It's a very application-oriented day. We can just use a calculator for them. All right. Now, inverse properties. Just think back to your composition. Remember composition of functions? Before I even get it. Remember composition of functions like f of g of x and g of f of x and that kind of stuff? Okay. So I'm going to just write something off to the side here. So if I had f of g at x, all right, that meant I put g of x into f, right? If I had a value, if I wanted like f at g at 2, that meant I put 2 into g, evaluated it and simplified it. Then maybe I get 6. And then I plug that back into f. You guys remember doing that? Okay, that was algebra 2, intermediate algebra, that kind of stuff. All right, we're going to use that same type of thing here with our trig functions. Now, here's just a list of rules for these. So sine, you can have the sine of the inverse sine of x, and basically they cancel each other out. All right, whether it's inside or outside, they're going to cancel each other out. Difference being, here, when I want sine, I have to make sure it's in this interval. When sine's on the outside, when inverse sine is on the outside, I have to go by the same interval that I just did before. Okay? Same way with cosine. When cosine's on the outside, I'm going to be on that negative 1 to 1 interval. When I have the inverse cosine on the outside, I have to go to the rules that we just talked about, where it's from 0 to pi. Okay? And this is all this is really going to be is kind of a check. You'll see we're going to do 3 of them here in a row. You just check. If this angle, if it fits within that range, you're good. If it doesn't fit within that range, it's undefined. That's it. Okay? Same thing with tangent as well. If tangent's on the outside, it works all the time. Tangent is the inverse tangent's on the outside, then it has to be on that set of intervals that we just talked about in the previous section. So we get down here. Cosine and inverse cosine of 0.6. So first off, we have the cosine on the outside. So I'm right here, cosine on the outside. Has to fit on the interval, negative 1 to 1. Is x between negative 1 and 1? Yes, it is. 0.6 is between negative 1 and 1, right? All right, so 0.6 is between negative 1 and 1, so I'm in good shape. Well, what does this say? If I have cosine of the inverse cosine of x, it's just x. So in this case, cosine of the inverse cosine of 0.6 would be 0.6. Done. Now, what happens if it doesn't fall within? So now I'm on inverse sine. Inverse sine is this guy right here. Okay, the inverse sine of the sine of x has to fall between pi over 2 and negative pi over 2 and positive pi over 2. In this case, does 3 pi over 2 fall within that? No, it does not. So it's not in the range. In this case, though, we can figure out the sine of 3 pi over 2, though, can't we? Because sine's in the inside, it's easier for us. If you reference that back to your unit circle, now I have this and the sine of 3 pi over 2. You probably don't remember it, but let's say you did off the top of your head. Sine of 3 pi over 2 is -1. So I can replace that with -1. All right, as soon as I replace that, now, again, I am still looking in that pi over 2, negative pi over 2 to pi over 2. So now I'm within that range, aren't I? So look back at my inverse sine chart. Inverse sine, it's up the top here. Inverse sine of -1. -1 is right there. Okay, so it's negative pi over 2. See how we did that? It was within the range of -1 to 1. Okay, so it fell within that range. So by this rule, if it's within the range and you have cosine on the outside, inverse cosine on the inside, it's in the range from 1 to 1. You just basically eliminate it as whatever that x is. Second one, though, was not in the range, so we can't just drop it all and say it's 3 pi over 2. Okay? Because that was not in the range, then we had to stop and say, can we simplify this? Sine of 3 pi over 2, we can simplify that. We got unit circle. All right, we can look that up. 3 pi over 2 is, what, straight down? Yeah, 1.5 pi. Yeah, straight down. All right, you can look that up. You get -1. So then we have -1. So now -1 is going to be in that range. Okay? I just look back to my inverse sine chart from that rule above. -1 paired up whenever sine was negative pi over 2. Okay? Now the last one, honestly, it's a little easier when the regular sine or cosine is on the inside. Okay? It's a little easier for us. So on this one now, we have the cosine of the inverse cosine of 1.5. Now, is this within the range of 1 to 1? It is not. Do we have a way to figure out the inverse cosine of 1.5 as it sits? No, it's not on the unit circle. It's not on our charts because it's outside the range. Therefore, undefined. All right, done. Right there, done. Undefined. All right. It was on the inside. If it was a normal cosine, we could figure that out. With a 1.5, not so much. Okay. So, first thing, check it. Is it in the range based off of the setup? Okay. Using these ones right here. Is it in the range? If it's in the range, basically you drop it and it's whatever that number is. Okay. It's not within the range. Can I simplify inside? If I cannot simplify inside, it's undefined. If I can simplify inside, simplify and replace, and then evaluate. With me? Okay, last thing of the day. What if I have composition of functions and they're two different functions? Okay? Not so much. Not so much. Okay? So we have to find the tangent, inverse tangent of 5 over 12, and then the cosine of that. All right? Now, first off, this is still just tangent, right? Inverse tangent. So inverse tangent, I can flip back here, and I'm worried about this range, correct? Is 5/12 smaller than pi over 2? Yeah, it definitely is. Okay? Whenever you have two separate ones like this, what you want to bring back is your just standard trig functions. Opposite over adjacent, opposite over hypotenuse, opposite over adjacent over hypotenuse. Bring those ones back to us. Okay? So now, this is within that range. We just want to look at it positive now, because this is a positive 5/12, right? So I'm looking from here to here. Therefore, this is positive. This is going to have to be in quadrant 1. So where is the tangent equal to 5/12? This becomes 5. This is my 12. Opposite over adjacent. Here's my angle. Okay, right here? All right, so let me do this again. Erase just a little bit. So we know that tangent has to be from negative pi over 2 to pi over 2, correct? Now, if we think about this on our unit circle, pi over 2 is right here, right? Negative pi over 2 is right here. Now, all students take calculus, okay? This thing is positive, right? The only way that this can be positive if it's in this it's in this guy, which changes that then from 0 pi over 2 to 0. You don't even have to change it to 0 if you don't want to. Just think it has to fall in those two quadrants. It's positive, it has to go in the first one. Yeah. All right. So you're all right with the construction so far? So we can find that theta, whenever we have theta, we have 5/12, because that's my tangent. Okay? Now, I want the cosine of that. So to find the cosine, I need adjacent over hypotenuse. So I just need to find the hypotenuse real quick, don't I? So I have a 5/12. It's a special triangle. Do you remember the third side? Hypotenuse has to be longer than the rest of them. Good, 13. I knew you were thinking that. Okay, 5, 12, 13. That's a Pythagorean triple. All right? So now this is kind of back more so to our function days, our composition of functions. So what is the cosine when the inverse tangent is 5/12? Well, what's the cosine of the triangle I just made here? 12/13. Because cosine of theta is 12/13. Guess what? I'm done. I didn't have to find the angle because I had an inverse trig function on the inside and a regular trig function on the outside. I wasn't worried about the angle. I just had to find the cosine when the tangent is equal to 5/12. Okay? I think these ones are honestly easier than the other ones. I mean, the other ones you got to sit there and check it. Is it in the interval? Yada yada. These ones just set up a triangle. Okay? Let's do one more and we'll call it done for the day. So I want the cotangent of the inverse sine of negative 1/3. So basically, what is the cotangent when the sine is negative 1/3? Remember, sine exists from where? Negative pi over 2 to pi over 2, right? So we're looking at quadrant 1 and 4 again. I have sine as negative, so what quadrant does that have to be in? That's be in the fourth. So my triangle is down here. Sine is opposite over hypotenuse, correct? Opposite is my top number of 1. Hypotenuse is 3. One of them is negative. It has to be the 1 because my hypotenuse is always positive. All right. Cotangent. Remember back to cotangent. Tangent is opposite over adjacent, so cotangent would be adjacent over opposite. Okay, so I'm going to need this side here. So let's do a little Pythagorean theorem. So let's go x squared plus negative 1 squared equals 3 squared. So I'm looking x squared plus 1 equals 9. Subtract the 1 over, so x squared is 8. Square root, x is 2 root 2. So this missing side will be 2 root 2. It's right, so it's still going to be positive, guy. All right, so I found where the sine is negative pi or negative 1/2, or 1 over 3. I can't read. We found where the sine is negative 1 over 3. That happens in this triangle right here. Now I just need the cotangent of it. So the cotangent of theta is going to be our adjacent over our opposite. Adjacent is 2 root 2, opposite negative 1. So therefore it's going to be negative 2 root 2. This is one of those lessons, I think, that can be a little bit tough because there's just kind of some finicky things. All right? It just if you get through those couple finicky things, it's really not terrible. All right? Just get past the checking the intervals, checking where it exists, those types of things. If we get through that and you can manage those couple checks right at the beginning, then the work's not that hard. All right? That's it for today. Now, tomorrow